we can move on to regular class. So I have sent you this one last night, my part. And this is the book. And we are covering the second half of the chapter 1 now. So I will restart from the 1.2 models of design, and we will cover 1.3 and up to end later on. Right. So this one is already, some part of this one, front part of this one is covered by Young-gi last time. Right. But I will restart again. So there are models of designs in this book, textbook, Method and Design, the procedural model. There are so many different models for designs, right, up to now. And problem solving, or we arrive at the general problem solver. Right? There is another model, okay? And then simulation, optimization, and design is also related. So there is a separate class about optimal design. Optimal design. Have you ever exposed to such a class? Optimization class? Two? Right. And then logic. Logic is from mathematics or philosophy. That is also related with design. And language, we already see that language is also related with design. And typology and design, this is what we call prototype. It is already told to you. So those are different, 6 different models of designs, which is covered in this book. And Young-gi covered 1 and 2. I will show you once again the procedural model. And we start from analysis and then go on to synthesis and then evaluation. And going loop and loop. So analysis is usually talking about market analysis. Okay? How can we design a smartphone for Indian ladies? Right? We should go to India to analyze the market there. Which one they like to buy, right? So then, coming from that market analysis, we can arrive at some list of requirements coming from the buyers. Right? Then we can convert that requirement into transformation into designs. So find solutions for that requirement. So we can say this is a requirement analysis. Something. And in this case, we go on to diverging. Everybody produce different designs, right? So it's diverging. And then evaluation cycle, we test all the options, different alternative designs, and arrive at to final or optimal design, right? So that can be a convergence cycle. So divergence and convergence is going on. And then do a do-loop. So that is a usual procedural model. There's another model called the goal decomposition. So we can divide and conquer. Divide and conquer. There's another topic. And conquer. What is the spelling? Conquer? Is it right? There is a famous phrase coming from programming, computer programming. Divide and make each modules and subroutines, components, and then combine together. So that kind of idea is coming in this way. Right? So after you arriving at final nodes of components, then you can create components or find the components to satisfy this requirement. Right? So temperature control, humidity, air movement, so that you can find small components and putting together, then you assemble to arrive at accommodation, home. That is the idea. Divide and conquer. And this is once again the sequential and cyclic procedural model, recursive process. And then each time you arrive at more detailed option, so that you already see this design spiral for the shipbuilding case. Okay. So that they do same design functions many times, but in more details. So arrive at this final design. So up to here is Young's portion already we covered. So this is coming to next subsection, that problem solver or general problem solver. They start from search to find exploring design space for potential solutions and also partial solutions. And then each search involves make decisions such as directions. So when I go for Busan city today, then I should decide which direction from here to arrive at the Busan, go on to right hand or left hand side or straight, based on goals and constraints. Goal can be the arriving at to Busan city. There are constraints that I should follow the rules of roads. And general problem solver, this is very simple case, similar to generator test, but this is another one. We start from current situation. I'm here. Right? Goal state can be arriving at Busan city. Current situation is I'm here. Right? Desired situation, goal can be arriving at Busan by today. Right? And then find out differences between two states. We call this is a gap. Right? I'm here in Daejeon. Goal state should be in Busan by end of this day. Right? There is a big difference, distance, right? And time. And choose action that change object or situation or status to bring the system closer to the goal. So I should go outside first, downstairs, take a taxi, go to station. Right? There are so many steps. So actions I can take. Right? And we call this is a general problem solver. So one step by one step, I analyze the gap and take action to reduce the gap. Right? It's simple. Right? Simple. So that computer can do this simple problem solving strategy. This is also similar to means and analysis. So this is a well-known problem of Tower of Hanoi. Have you ever played this game before? Yes? You know what? Okay. I don't know it. But anyway, they want to move these circular shapes into another place, right? Another place. Move with minimum actions, something like that, right? So general problem solver. So final goal state may be the same shape in this position, something like that. Right? That could be formalized. So your word. It cannot be applied direct, but the idea can be used for this. And then the search of a combination of all the cases can be big. But anyway, this one, the deep blue, is a computer coming from IBM. And this is specialized for chess playing computer. In 1997, 20 years ago, the machine, the Deep Blue beat the world champion coming from Russia 20 years ago. And then last year, or 2 years ago, the AlphaGo beat the Go player, world champion Go player. So but this one choose such a GPS strategy, one step by one step. But as I told you that they have been to two strategies. One is using algorithm. The other one is just simple, how can I say, speed or machine performance. Performance means big data and big memory and high speed calculation. That is good for computer, right? So algorithmic approaches, they try to find a very complex software algorithm that is simulating humans playing method, right? But the other one is Deep Blue chooses just try all possible combinations and test. Try all possible combination of chess. So when the chess game is arriving in the middle, analyze the situation and try to choose next step. But there's so many combinations of possibility. Where the machine calculates all possibilities, right? At the time. So that means the simple and many calculations. That is good for them. Another strategy is optimization. So simulation is trying to emulate the physical world, right? Simulation, by using computers. So why? They want to predict the performance of a given design. Right? The concept car for the next year is only in the concept, and also it can make a sketch, right? And then using the sketch, you can convert into computer model and then do analysis, finite element analysis, or computational fluid dynamics, cost analysis, durability, any other things. Right? So that kind of thing is a simulation, all simulations. Computer simulation of structural performance or hydrodynamic performances and economic performances. And then optimization find given, we call this is objective function, performance goal, objective function. So when I try to design a steel pipe which can sustain 500 kilogram force, and then my objective can be the minimum weight of this, or it can be a minimum cost, depending on my situation. Right? So we call this is a given performance, minimum weight, minimum cost. But the optimization algorithm should find out the best solution of it. So here, a keyword in optimization is objective function, constraint functions, and performance variables, and decision variable. This is objective function. Right. So the goal state, right? And then there is objectives. There can be several objectives: cost, or weight, or there is no weight, but thermal, lighting, acoustic, there are different goal objectives. And performance variables can be, say, here, the length and diameter and thickness of the pipe, plate. That kind of thing can be performance variables. So by choosing by changing these variables, you can arrive at different designs. Right? Among them, you should find the best one. And then there is a relationship. And decision variable, the performance is arrived at. So we should choose among them. Right? This is performances. So in optimization, the performance criteria, the objective function, used to guide the search through the state space. So among them, this is design space, right? Design space. So among them, we arrive at this best solution here. Right? But starting from here, we arrive at search and then find out, arrive at this. That is the wish I want to do. So that is similar to such a guided search in optimization algorithm. Right? So in here, it has both synthesis and evaluation. So population of options, optional design alternatives, and then evaluate each of them, and then find out the best one. Right? This is optimization. So by synthesis, that means they are changing the design variables. Say, I can choose, say, 20 centimeter, 21, 22, 23 of length, and diameter can be 1 centimeter, 1.1, 1.2, 1.3. Right? And thickness can be 1 millimeter or 0.9 millimeter, 1.1 millimeter. There are so many design variables can change, right? Optional changes. And then by combining those numbers, you arrive at different designs. Right? So that can be a population of alternative designs. And then evaluation gives you which one is most minimum weight or minimum cost. But still, you should sustain the forces, weight, without breaking. Right? So that can be the constraint. No failure under 500 kilogram force. There's a constraint. Right? So you should evaluate with using the constraint. So in simulation, they don't have such a population of new designs or constraint. They just emulate a physical system to arrive at performances. So that is, evaluation is involved in optimization process. Optimization is powerful, but the problem is you should have a mathematical equation somewhere. Mathematical form, we call this is formulation. Otherwise, the optimization algorithm cannot work. Somehow, not single equation, but computational model should be arrived at from your problems. Say, I want to design a new smartphone for Indian ladies. How can you change that problem into computer programs or formulation, mathematical formulation? Then optimization can handle this. Right? There is one weak point of optimization. Logic and design. There is a formal logic, and then design is a process of making logical deduction. Already we told about this one. And set of design requirement. We begin with the axiom and design requirement. That is similar to design requirement and process in inevitable course of theorem. And so that there is a person who arrive at, we call this is axiomatic design theory. Axiomatic design method, design, another design model called axiomatic design. So that he has been a president of this KAIST. He was in MIT, so Korean, American. So he has been a president of this school for some time. But he arrived, so he say, he find that design model is somehow resemble a mathematical, or he say we can make a design problem into mathematical formulations of problem. And constraint satisfaction model. Constraint is coming from optimization. Say that we should say sustain the 500 kilogram force. That is a requirement, a constraint requirement. As far as you sustain, find out minimum weight or minimum cost. Right? Here, the building design. This is a building design, but there is a rules, regulations coming from social law that require the setback from the boundary. So when I have a area of land and I want to build my building as big as possible, right? Tall, big, possible, within the area of given land, right? But there is a regulation that from the street there should be a minimum required setback, right? And then there is also height limitation from the area you can calculate or regulation. And then from the overshadowing from the nearby neighborhood building, the requirement coming from the overshadowing. Right? What this one? Right of way, this is similar to this one, setback. That kind of constraints, regulations gives you already the final design, right? No more, because I want to make as big as possible. So the design of shape of the building is already fixed, only by constraints. Language and design. All right, let's see this. Linguistics is concerned with the generation and interpretation. Generation of sentence. And then after generating a sentence, we can interpret that sentence. Right? And we can use for the generation of sentence vocabularies as a component of the car, and composition, combining, and style, and context, and meaning. Right? Context and style, you can say that I want to design a smartphone for Indian lady, right? That is the context. Right? And also we find our style. Right? Compositional rules. How can you combine the Lego blocks, grammatical rules, and that is applicable for configuration of components in a design. Right? Say that arrangement of gears and pulleys in a mechanical device is this is a linguistic. We already see this one. Right? So this is a sentence, and then noun phrase and verb phrase. Noun phrase is made of determiner, nouns, and verb phrase is made of verb, determiner, and nouns. Right? The boy eats the apple. So the parsing of the sentence, interpretation, typology. Design begins with a prototype, Boeing 747, and the progress to specific designs. So design involves instantiation of prototype. It is very similar to a class and instance in object-oriented programming. They are saying about class and instance. Something like a C++ is they are saying object-oriented programming language, right? And they are talking about class and instance. And class is about generalization, right? We call it the generalization. And in this case, specialization. Specific, very specific. Here is one specific item I bought 1 year ago, right? But there are so many same products in the shop. I can choose, right? So all items of same product is we call a class of laser pointers. But this one is specific instance, which I bought from the shop. This is mine, right? This is all classmate. So we call this as a kind of class of student, right? Student class. And then specifically each person has his own name and identification. Right? So we call it abstraction is similar to generalization. So upper level is we call abstract and general. So class hierarchy of abstraction is goes on. So generalization we go on to this kind of hierarchy. So we call this more abstract and general, more specific specialization. Right? Design is a process of instantiation. It's making a specific design, right? I want to arrive at specific design, which sustain force, but minimum weight, right? We arrive at specific instance. Proceeding from a class description to arrive at a specialized instance. So starting from a prototype, Boeing 747, and progressively refine in a response to a practical context. And go on to knowledge and design, the subsection, another subsection. The design models are finished. We already see the 6 models of designs. Knowledge and optimization. Once again, optimization coming. And syntax and semantics, and design space, and design knowledge. What is design knowledge? And generic design, prototype again, and knowledge-based design. So previously we talked about design itself. Now we go on to the knowledge of design. So this is a design variables. Say length of this one. And can be diameter of this one, diameter of this pipe, right? Length, diameter. There are different alternatives, say 10 centimeter, 11 centimeter, 11.2 centimeter, and diameter also different. Right? And then if I arrive at this decision variables, then that correspond to the weight of this pipe design or the performance of structural safety. We arrive at different performance spaces, but maybe this one can be weight. So this can be a mapping. This mapping we should use analysis tools. Weight estimation. Oh, there is 2 performance. So it can be a weight, it can be a cost, or the others, or strength. So optimization again. In knowledge-based system, the knowledge must be explicit because we want to use computer. Computer should be somehow. The design itself, also knowledge itself, should be typed into the computer, into database. Right? So it should be explicit. They can be inspected and understood independently of the way in which controlled. Controlling is using this one. So knowledge is represented here, explicitly represented, and then we can use this one to solve the problem. We call this as controlling. Central idea is separation of control. Control is reasoning. There is also another reasoning engine. So, reasoning engine. Reasoning. Or we can say simply chaining, knowledge chaining, forward chaining, backward chaining, or reasoning, and control. This is a control of knowledge. Control of knowledge, reasoning, and also knowledge base, domain knowledge, right? Domain knowledge. Fact database and rule base. Questions? Okay. No question. Then we move on to, who is it?